Good morning, students. Today we will be discussing unified field theory. But before going to unified field theory, we will have a quick review of the four fundamental forces in nature. We have already seen these fundamental forces. We will have to explain a little bit in detail regarding the weak nuclear force. We have seen the other three forces. So all the forces that we see around us are one or other type of one of these fundamental forces. So we saw that the first one is gravitational force, which is always attractive and which is responsible for the attraction between planets, satellites, and also it can explain the large scale phenomena of the universe, such as the formation and evolution of stars. And it is universal, which means all the objects which has mass will have gravitational force. And we also learned that scientists believe it is due to the mutual exchange of a type of particle called graviton, even though it is not experimentally proved. And then we have another kind of fundamental force called electromagnetic force, that is the attraction of or repulsion between two charged particles. It can be two types, that attraction or repulsion, because we know that the charged particles are either positive or negative. But gravitational force is always attractive because mass is only of one kind. Now, the range of both electromagnetic and gravitational force is very large, it is infinity. And whatever force we are seeing around us other than gravitational force are electromagnetic nature. Suppose frictional force, contact force, spring force, elastic force, all of them are basically electromagnetic in nature, because all these matter is made of atoms, and atoms themselves are made of subatomic particles like electrons and protons, which are positive and negative and positive in charge. And this electromagnetic force exists between charges due to the exchange of massless chargeless particles called photons. Then we saw the strong nuclear force. You must have wondered before why the protons, which are positive in charge, stay together in a short space inside the nucleus. They are supposed to repel each other. Now, why they are not repelling each other? Because there is a strong nuclear force which is 100 times the electromagnetic repulsion between them. And this force comes to play if they are very close to each other, because the range of the strong nuclear force is around 10 raised to minus 15 meters, which is about the dimension of a nucleus. So if they are very close to each other within a nucleus, the dominant force is strong nuclear force. Therefore, they remain close to each other. And this strong nuclear force is independent of charge. It acts equally between proton and proton, neutron and neutron, and also between proton and neutron within a nucleus. But when the protons are apart, more maybe around 10 raised to minus 12 meters apart, then the strong nuclear force will have no role. Then the electrostatic repulsive force will dominate and the protons will move apart or repel. So if they are very close to each other within the nuclear dimension, then only the strong nuclear force will come to play. And then we saw that another kind of fundamental force is called the weak nuclear force, which will not be very familiar to you. Now, weak nuclear force is the short-ranged and short-valued force which acts within the fundamental particles of nucleus to make the nucleus unstable. You have learned in lower classes that certain nucleus, especially large ones, are unstable. They are unstable and they undergo a process called radioactivity, whereby unstable nucleus will give away radiations which are called alpha, beta, and gamma radiations, and they will come down to a stable stage. So these alpha radiations are positively charged. It contains two protons and two neutrons. So they are positively charged and have high mass. Another kind of radiation which is given out is called beta. What is meant by beta decay? A beta particle is negatively charged. But do the nucleus contain a negatively charged particle? Is there a negative charged particle inside the nucleus? No. What are they? Only protons and neutrons. So how can it give away an electron or a beta particle? What happens within the nucleus? So here you have the answer. A neutron gets converted to a proton, an electron, and an anti-neutrino. This is an anti-neutrino. So a neutron gets converted to a positively charged proton, a negatively charged electron. So the positive and negative charge, they have equal magnitude. So the total charge will be 0 or neutral, that is equal to the charge of the neutron. Now, why there is a anti-neutrino along with the electron? When a particle changes to another particle, the number of particles should be conserved. Here you can see that this is a neutron, so one particle, but it gives away three. So this is a particle, proton, electron is another particle. So in order to conserve the number of particles, it gives away an antiparticle. This is an antiparticle. It is called anti-neutrino. It is a chargeless, massless particle, and it conserves the particle number. So here this has a particle number plus 1, this has a particle number plus 1, this has a particle number minus 1 because it is antiparticle. You need not go deep into it. It's related to particle physics, which you haven't learned so far. So we have an anti-neutrino coming along with the beta particle or a electron. So when this beta decay occurs, the force which is responsible for that is called the weak nuclear force. So what is weak nuclear force? It is the short ranged and short valued force which acts within the fundamental particles of a nucleus. Is this clear to you? What is a weak nuclear force? Did you get some idea about that?
Teacher,
Yes.
if a particle doesn't have mass, doesn't have charge, then how can it exist?
There is a slight mass, very small mass. And the mass of a anti-neutrino or a neutrino is determined only in 2015. There is a mass, but negligibly small. That is why we
Okay.
call it a massless particle. There are many fundamental particles which has very less mass and they are very short-lived also, but they are identified with good technology. So neutrino is one of them. Not
Okay.
completely massless. I mean, negligible mass, very small mass. Now, it appears only in certain nuclear processes such as the BKDK, as I explained now, and the nucleus emits an electron. This is a beta decay. A nucleus emits an electron and an uncharged particle called antineutrino. Now, beta decay can be of two types. One is this. It emits an electron and an antineutrino. There is a rare case of other kind of beta decay where it emits a positron. Positron is the antiparticle of electron. Along with that, it will emit a neutrino, which is an antiparticle of antineutrino. So that again, the particle number is conserved. So no need to go deep into it. Just understand that weak nuclear force is related to this.
So the electron it emits will go to the orbit or it will stay in the nucleus.
It depends upon the energy of the electron. Sometimes it will go to the orbit and it will kick out an electron from the orbit.
That means the electron number will change, right?
No, electron number cannot change.
Oh,
That's
it
what
says
I told.
preserved. Yeah,
It will go to the orbit, then it will kick out an electron, or it will
another one.
directly go out. It depends upon the energy of that electron which is coming out. And it is not, even though it is mentioned weak nuclear force, it is not as weak as the gravitational force, but it is weaker than the electromagnetic and the strong nuclear force. Strong nuclear force is the strongest among the fundamental forces. Now the range is extremely small. It's around 10 raised to minus, oh, it should be 10 raised to minus 18 actually. I'm sorry, this is a typing mistake. It's around 10 raised to minus 18 meters. See, the range is still smaller than that of the strong nuclear force. And it is due to the mutual exchange of gauge boson particles. So these, there are certain fundamental particles called gauge boson. The weak nuclear force is due to the mutual exchange of gauge boson particles. This again belongs to the particle physics. The gauge bosons which are responsible for the nuclear forces W and Z gauge boson. So you will not be learning in detail about that. Now, let us see what is meant by, or let us make a quick comparison of the fundamental forces. There are four of them: strong, electromagnetic, weak, gravity. You can see according to what they are arranged here. According to what? They are arranged according to their strength. The
Strong.
strongest, yeah, the
Um,
according to strength. So the strongest one is strong nuclear force, then comes electromagnetic, then weak nuclear force, and then gravitational force. Now, strong forces acts between protons and neutrons. If you consider its strength as one, the strength of electromagnetic force is 1 by 3, 137. And the strength of weak nuclear force is 10 raised to minus 16, and that of gravity is 6 times 10 raised to minus 39. See how weak is a gravitational force compared to the strong nuclear force. Now, the range, see, for strong it is 10 raised to minus 15 meters, and for electromagnetic force and for gravity the range is infinite, and then for weak nuclear force it is 10 raised to minus 18 meters. Now the particles, fundamental particles which are responsible for the strong nuclear force, they are called gluons. Gluons, because the strong nuclear force acts between protons and neutrons. They themselves are made of quarks. That is another fundamental particle. So protons and neutrons are made of quarks, and these quarks, uh, the particles which are responsible for the interaction of quarks is gluons. So gluons is the particle responsible for.
teacher,
Yes.
in the textbook, it's written that weak nuclear force has a range about 10 raised to minus 16.
That's what I am telling you. It is 10 raised to minus 80.
It's a mistake in the textbook also.
Yeah, yeah, yeah. It will be around 10 raised to minus 80. Then it will be, it was much smaller than that for the, they have told within 10 raised to minus 16 to 10 raised to minus 18, not exactly 10 raised to minus 16. They have mentioned earlier in the detail, in the text, they have mentioned it is within 10 raised to minus 16 to 10 raised to minus 18. So the minimum range, we have to focus on the minimum up to which it can go, right? So that is 10 raised to minus 18. Then the particle responsible are the gauge bosons. They are W and Z bosons. And for gravity, it is graviton, but we haven't experimentally discovered graviton. The other particles are experimentally discovered. So that's all about fundamental forces. Now let us see what is meant by unified field theory. Now, unified field theory is a theory used to express the four fundamental forces by a single theory. So to express the four fundamental forces by a single theory is called the unified field theory. It's not yet complete. It's not yet complete. What we will be discussing today will be few events or few landmarks towards the unification of these fundamental forces. So starting from Newton, we will just go through few events or few discoveries which are landmarks towards unified field theory. It's not yet complete. So let us start with Newton's discovery. Isaac Newton discovered the law of universal gravitation and unified the celestial forces with the forces of gravity. So what is meant by gravity? What is meant by gravity? Gravity usually refers to Earth's attraction of materials. So celestial forces means the attraction between the planets, between the satellites, and also between the different things in the solar system, the galaxies, are all the celestial objects out there in the universe. Earlier, it was thought that is a totally different phenomenon, and what we experience as an attractive force towards Earth is different phenomenon. But when Newton discovered the universal gravitation, that is a common law which is applicable to both. So he unified the celestial forces with the forces of gravity. That is the force of attraction that we experience on Earth. Later, James Clerk Maxwell discovered the electromagnetic theory and unified electricity and magnetism. Until Maxwell discovered this, it was thought that electricity and magnetism are totally two different fields. But later he found that uh, light and other electromagnetic waves are a combination of electric field and magnetic field. We have seen this in our previous chapters. So, and also he put forward few equations called Maxwell's equations, which are applicable for electromagnetic waves. So that completes the unification of electricity and magnetism. Now, when we come to more recent or to the modern physics part, notable event is that in 1967, Abdus Salam, Professor Abdus Salam and Steven Weinberg independently completed Glashow theory, started by Sheldon Glashow in 1961. This is known as electroweak interaction theory, and it unifies electromagnetic force and weak nuclear force. So we saw electromagnetic field or electromagnetic force as one kind of fundamental force, and weak nuclear force as another kind of fundamental force. So Sheldon Glasgow started his studies in 1961, and he was trying to unify these two fundamental forces. The ultimate aim of physicists to try to explain all the physical phenomena that we see around it with the minimum number of laws. Okay, so we are trying to get more generalized. Even if we can explain all the phenomena with one single law, that will be the best. That's the ideal situation. That's what physicists are trying to achieve. So these are all steps towards it. So this is electromagnetic weak interaction theory, means that a theory that connects electromagnetic force and weak nuclear force. And they identified this W and Z gauge bosons that are responsible for the weak force. And for that, these three persons, that is Sheldon Glashow, Abdus Salam, and Steven Weinberg received Nobel Prize in 1979. Is this clear to you? What is unified field theory and few events related to it? So let me continue with the story of unified field theory. Later, in 1979, a group of 100 physicists at CERN, that is the European Organization for Nuclear Research at Geneva, under the leadership of Carlo Rubbia, this is Carlo Rubbia, and Simon van der Meer, this is Simon van der Meer, they discovered W and Z gauge bosons, which established electroweak theory, which was put forward before by Glashow and his team. So they received the Nobel Prize for discovering experimentally this W and Z gauge bosons. And they received the Nobel Prize for that in 1984. So here, see, we are coming to the modern physics world and particle physics. So when we go deeper into the unification of different forces, we come deep and deep into the particles. So we are dealing now with smaller and smaller particles having negligibly small mass and very difficult to identify. And later, in particle physics, all over the world, all the particle physicists all over the world are working to unify the strong nuclear force and electroweak force. It is not yet complete, and their attempts are entitled as grand unification theories. So they are still trying that. And recently, in 2015, the Japanese scientists Takaki Kajita, this is Takaki Kajita, and Canadian scientist Arthur B. MacDonald were awarded Nobel Prize for determining the mass of neutrino. Remember, I told neutrino or antineutrino as massless, chargeless particle. That means their mass is negligibly small, and they have discovered or they have determined its mass in 2015. So they are very tiny particles, fundamental particles, and their mass is very small. I don't know the value of its mass, but they discovered it in 2015. Now, let us see as a whole what are the efforts towards the unified field theory. See, first it started with electricity and magnetism unified to get electromagnetism. Who did this? Are you all there? Who did?
Yes,
Okay, who did this? Electricity and
Maxwell.
magnetism? Yes, Maxwell. So after Maxwell, electromagnetic force and weak force was unified through electroweak unification. Do you remember the name of the scientist? Do you remember the name of the scientist who did that?
Abdul Salam. No,
Yes, Abdus Salam,
I've got
Sheldon
that.
Blasco,
Yeah, that name. So hard.
and then Steven Weinberg. So these three scientists have unified these two, and they have put forward the weak electroweak unification. And now the scientists are trying to unify this with the strong force, and the efforts are called grand unification. And there are short theories which are not established. So all those theories are together called grand unification theories. And see here, the gravity is out of the jurisdiction of all these efforts till now. They are in this effort. So gravity, it didn't come to play yet. So after they find a unification with the strong force, their then efforts will be to unify gravity. So we will have to learn only one theory or one law related to all these fundamental forces when they are all unified together. And see the range going down deeper and deeper. See the distance reducing from 10 raised to minus 14 to 10 raised to minus 16. It's in centimeters. So if you are telling in meters, this will be 10 raised to minus 16 to 10 raised to minus 18 to 10 raised to minus 32 and then to 10 raised to minus 35. So we have to go deeper and deeper into the material to learn more about that. See, all this related in Nobel Prizes. Do you want to get any Nobel Prize? Are you interested to go in the field of physics? Is there anyone out there?
No.
No, no, none of you.
So we don't have that capacity.
You have
Zaman,
that
zaman.
capacity. You are just learning the things now, right? So you can be scientist and you can go in this field. See, and if you find something very remarkable, sure you will get a Nobel Prize. So here, let us see what are quarks. Do you remember what are quarks? Quarks.
Particle of strong, that
Yeah,
one.
particles upon which strong nuclear force acts. Excellent. So, quarks are the particles upon which strong nuclear force acts, and the protons and neutrons are made of quarks. There are different kinds of quarks. Actually, there are six kinds of quarks, but the two kind called up quark and down quark make up protons and neutrons. There are other quarks like charm, strange, and all that you are not going in detail to it. Then all these quarks, see together, up and down quarks are called quarks. And then leptons and neutrinos are there. Electron is a charged lepton. So these comes under the particle physics category. So electron is a charged lepton. So there are other neutrinos. Neutrinos are uncharged. We so along with the electron, anti-neutrino is formed, right? So a lepton and a anti-lepton. So the lepton number gets cancelled when a neutron gets converted to proton, electron, and antineutrino. So those kinds of particles are called leptons. So if we are able to combine or unify these leptons and particles made of quarks, which are usually called hadrons, if we can combine them, they can be called leptoquarks, and we can unify all the fundamental particles, all the matter existing in the universe. So basically, all the matter which exists in the universe are made of quarks, neutrinos, or leptons, fundamental particles. So the effort is to unify all these particles. Is it clear to you? Is this clear to
Yes,
you?
teacher.
Okay. So